In this video, we are going to look at some basic trig identities here. And we're going to start with these. These are very simple identities, but even these help you do quite a bit. So these are the reciprocal quotient identities, and it's basically taking the trig functions other than sine and cosine and breaking them up into sine and cosine. So tangent of x, which was y over x, you can write as sine x over cosine x, because sine x is equal to y, cosine x is equal to x, so that would be y over x. So that's an identity. Secant, similarly, can be written 1 over cosine. Cotangent can be written cosine over sine, and cosecant can be written 1 over sine. Okay? Then you have the even-odd identities, and this is something you can use to simplify trig functions when they have a negative number inside the trig function, so like a negative x. So basically, for cosine and secant, you can just drop the negative sign, and the reason is because those are even functions. They're symmetrical about the y-axis, so they're the same on both sides. So it doesn't matter if it's negative or positive, just drop it. Okay? The other 4 trig functions are odd identities, and that means they're symmetrical about the origin. And what that ends up meaning is that the sine of the opposite of x is equal to the opposite of the sine of x. And so the feel of this, it's kind of like a rule where you can take a negative sign and pull it on the outside. You can pull it to the outside in front of the function. So sine of negative x, just pull the negative sign out and you get negative sine x. Or tangent negative x, just pull the sign out. So on. Okay? So let's use these just to see how you can simplify expressions. So even these simple ones here, these simple identities can allow us to do quite a bit. So let's say I have this inside of a problem. Well, I can pull the negative sign out, and that turns the minus sign into a plus sign. And so what I get is sine x plus sine x. And those are common terms in, so I could just write that as 2 sine x. So that simplifies down quite nicely. So what about this? So I can take that negative sign and I can move it out, and I get negative cosine x tangent x. Now the tangent using the reciprocal identity can be written sine over cosine. And so I could rewrite this negative cosine x times sine x over cosine x. And basically then these are going to cancel out, because this is like negative cosine x over 1. These will cancel out, and that just gives me the opposite of the sine of x. So again, that simplifies down quite nicely. And so what about this one here? Well, I can pull the negative sign out again, and if I do that, I get tangent x plus cotangent x. And then I can write these as the reciprocals of sines and cosines. I can write them in terms of sines and cosines. So I get sine x over cosine x plus cosine x over sine x. And now I just want to remind you to add these together. You're not going to like add numerator, add denominator. Okay? When you add 2 fractions, you got to get a common denominator. And the common denominator will always be the product of the 2 denominators when you're dealing with algebra expressions like this. And so to convert these, okay, this would be, I got to multiply the top and bottom by sine x, right? And so this would be like sine x, and then sine x, cosine x, plus, and then here I got to multiply the top and bottom by cosine x. So I would get cosine x over cosine x times cosine x over sine x. Okay? And so when you multiply these two together, that would be like you could write it sine x, that quantity, squared, plus cosine x, that quantity, squared, all over sine x, cosine x. Now, if you've been doing trigonometry for a while, then I'm adding some extra steps here. So I'm just doing this for maybe some of the people that don't have as much experience. So a way of simplifying this is just writing that sine squared x, and then this would be cosine squared x. All of that over sine x, cosine x. Okay? And so you don't have to include this middle step. If you're going to multiply these two together, you can know that that's cosine, or that would be sine squared x. Okay? You just have to be careful that you know what that means, that it's a sine x times a sine x. Okay? Another thing, to get this common denominator, there's an easy way to do it. You don't have to write this all out. Let me show you what it is. In fact, I won't use this. Well, I'll go ahead and use that just to show you. Let me actually change it. A over B plus C over D. This is what I was wanting to write. So the easy way, the common denominator will be B times D, and so you'd be multiplying the top and bottom by D here, and the top and bottom by B here. So what you can do is you can just take the A times D plus this sign plus the B times C, and then put that all over B times D. Does that make sense? And that's just a nice easy way. So I would have went from here directly to here, and I would have done it by saying sine squared x plus cosine squared x all over cosine times sine of x. Okay? That's how I would have done it. And I just showed extra steps here. Now, something we don't know yet, but it's the next thing we're going to learn, is that whenever you have a sine squared x plus a cosine squared x together, that is the Pythagorean identity, and sine squared x plus cosine squared x is just equal to 1. So I could rewrite this as 1 over sine x times cosine x. Okay, and as it turns out, you can move both of these here to the top. This is, well, let me just show you. This is like 1 times sine x times 1 times cosine x, right? And then those two, using the reciprocal identities, would be cosecant x times secant x. Okay, so that's a nice sequence there. If I have, a tangent plus a cotangent, that's equal to cosecant times the secant. So the addition of these two is the product of those two, which is an interesting relationship. Okay, so those are just some of the basic trig identities. So now let's look at this Pythagorean identity that I actually ended up using there. Here's the idea. Okay, so we're defining these in terms of the unit circle. So if you go a certain theta, like that, then you stop, you get this point on the unit circle. Well, the cosine is equal to the x, and the sine is equal to the y, right? But all these points on the unit circle here satisfy the equation for a unit circle. So this ordered pair, if I put the x there and the y there, it'll equal 1, right? Well, the x here, if it's on the unit circle, is the cosine x, right? And the y is the sine x, right? And so that would equal 1. And then to simplify it, using the notation, we would get cosine squared x plus sine squared x is equal to 1. Sorry, and I'm using theta here. So let me change those to thetas. Okay. So the x is equal to cosine theta, right? and the y is equal to the sine theta. Okay, so this is that Pythagorean identity, and that's the basic one. And so I'm going to write it down here, but I'll write it in terms of x, because these identities oftentimes are written in terms of x. This is just a placeholder. This is not the x on the unit circle. This is actually playing the role of theta here. So that's the first Pythagorean identity, but you also have two others that you can use as well that are handy, and they actually come from this one. And so let me show you how this works. If you understand how it works, you almost don't need to memorize these. So once you have this one, if I multiply through by the cosine squared x, that would make this cosine squared, or cosine squared theta. That would make that cosine squared theta, this cosine squared theta, and this cosine squared theta. Well, this is just 1. This is tangent squared theta, and this is the secant squared theta. Okay, and so basically multiplying through by cosine gives you this identity: 1 plus tangent squared theta is equal to secant squared theta. Okay, and you could do something similar by multiplying each one by sine squared theta. And if you do that, then you'll get the cotangent squared. I'm using theta here now. I should have been using x. Sorry about that. To be consistent up here. And this should be cotangent squared x plus 1 is equal to cosecant squared x. Okay? And so these are your three main Pythagorean identities. And then you can use them in different ways. Like if I have a sine squared x in a problem, and it's useful to rename it this, I can do that, because basically I just moved the cosine to the other side, right? And so if I have that in the problem, or if I have this in the problem, I can change it to this. Okay. Similarly, I could do secant squared x minus 1 is equal to tangent squared x. So I could use something like that. Or I could just bring the secant squared, or the tangent squared x to the other side, and then what I would get is secant squared x minus tangent squared x is equal to 1. So you'd get another sort of identity. So you could do all kinds of, you could rearrange these, and that could be used in different problems in different ways. Okay, so now I just have a couple problems involving these Pythagorean identities. So let's look at this. So basically I got this expression. It looks pretty complicated. Let's see if we can simplify it at all. So what I'm going to do is I'm going to put it over a common denominator. So I'm going to multiply these two, and I get sine squared x. And then I got a minus here. And then I'm going to multiply these two. And so that would be cosine x times 1 minus cosine x. And all of that will be times the product of these two. So it would be 1 minus cosine x times sine x. Right? So that's pretty complicated, but now I can distribute the cosine over this. So that's what I'm going to do. Sine squared x minus cosine x, and I got to bring the negative with it, plus cosine squared x. And all of that will be over 1 minus cosine x times sine x. Okay, now I can bring these two together, and then I get sine squared x plus cosine squared x, and that would just equal 1. So just by commuting that around, I get 1 minus cosine x all over 1 minus cosine x times sine x. And now this actually is a common factor. You can cancel that out, and you would get 1 over sine x. And that just becomes cosecant x. So that complicated expression simplified down very, very nicely. Now let me also draw attention to the fact that when I did this, each step is equal to the previous one. Okay, and sometimes it takes a lot of extra work. Like this is a lot to write out. But I didn't just kind of distribute that over and just write the top there and forget this and then bring it back in over here, so that if you were to actually check each of these, they're not really equal. Okay? Now you might, when it's simple, you might be able to hold it in your mind and still get there without making a mistake. But it's by doing that sort of thing that mistakes come in. And as it gets more complicated, it's almost impossible to hold it together. Okay? You just have to write everything out. Even if it takes extra work, you just write it out. Okay? And that way you're guaranteed that this is equal to this, that is equal to this, that is equal to this, which is equal to that, which is equal to this. And so now I know what I started with is equal to the cosecant x. You really want to take time. Don't be lazy. Take time and write it out. Okay? So now, in this problem, this other example with the Pythagorean identity, what I have is cosine theta is equal to negative 2/5. That's what I'm told. I'm also told that theta is in the third quadrant. Right? So, the third quadrant is like down here. Right? And like negative 2/5 would be maybe right here. Negative 2/5. Ooh, not there, sorry. Made a mistake here. I'm just going to scribble this out. And the mistake I made is the cosine is the x-coordinate. So I'm in the third quadrant here. And the x-coordinate is negative 2/5. Okay? So the x-coordinate is right there. Right? And so whatever this theta is, it's that there. And I know the x-coordinate is negative 2/5. Now what it wants me to do is find the value of the other 5 functions. Okay? Well, if I knew the y value in this quadrant, I'd be good to go. I'd have x and y, and I could find all the values. Okay? So here, the Pythagorean identity can be helpful, because I know that, cosine squared theta plus sine squared theta is equal to 1, right? And cosine squared theta is just the cosine, that quantity squared, plus sine squared theta is equal to 1. And the cosine theta is equal to negative 2/5. So I get negative 2/5 squared plus sine squared theta is equal to 1. And now I can solve for the sine of theta here. So this becomes positive 4/25 plus sine squared theta. That's equal to 1. Now I'm going to bring this over. This will be 25/25 minus 4/25 means I get sine squared theta is equal to 21/25. And then I'm going to take the square root of both sides. That will be plus or minus the square root of both sides. So I know that sine theta is equal to plus or minus the square root of 21/5. Okay? And so the question is, which one is it? The positive one or the negative one? Well, it's in the third quadrant, and so the sign has to be negative. That's why it's important to know what quadrant the theta is in, right? So it's going to be negative. So this is negative square root of 21/5. Okay? And now I have the x and the y, so now I can find the other trig functions, right? So I found that sine theta is equal to negative square root of 21/5. The tangent of theta is going to be the y over the x. So it'd be negative square root of 21/5. All that, or negative 2/5. Okay, so then I would invert and multiply. The 5s would cancel out, the negatives would cancel out, and I would get square root of 21/2. And that's what I would get in that case. Okay, the cotangent of theta Well, the cotangent of theta is just the reciprocal of the tangent. So it might be easier just to do 2 over the square root of 21 as opposed to flipping those and redoing it. Okay? But then I want to rationalize that denominator. So I get 2 square root of 21 over 21. Okay? The secant of theta, this is just going to be negative, the reciprocal of negative 2/5, so it's negative 5/2. Okay, and then the cosecant of theta is the reciprocal of negative square root of 21 over 5, so it would be 5 over square root of 21, which will be negative 5 square root of 21 over 21. And so there you go. These are the other 5 trig functions. Okay, so if I'm given one of the trig functions, you can actually do this for, it doesn't matter which trig function you got. You would just, if you were given, like, let's say secant, you would use the identity for well, if you were given secant, you could just change it and make it into cosine. There you go. That's probably the easier way to do it. But I was going to say you could use the Pythagorean identity that involves secant and tangent and go from there. Okay, so those are some nice problems. You actually have some of those on the homework, which is why I worked all that out. But it's a nice application of the Pythagorean identities. Okay, so now let's finish with this. This is the sum difference identities. This plays a big role in calculus because you actually need it when you're finding the derivatives for the trig functions. It's a rule that you need in order to do that. So what I've done is I've written these out, and I've actually written these out so that I have the sums and the differences as separate identities. So what I mean by that is, let's see if I can find an example. Like I've written some out here and I decided to change it, but like what they do oftentimes in textbooks is if this is a plus minus and this over here is a plus minus, and if this is x plus y, then this will be this plus that. But if this is a plus minus and this is a minus plus, then if this is a positive here, it's a negative there. If it's a negative here, it's positive there. So this identity here, if this is plus, that'll be plus and that'll be minus. If it's minus, this will be minus and that'll be plus. So whichever one is on top over here, you use the top one over here. Whichever one's on bottom over there, you use the one on bottom over here. Okay? I don't know if I said that right, but hopefully that made sense. But I kind of like writing it out like this so that you have the sine, sum difference identities, the cosine, and the tangent. And I'm just, writing it out a little more clearly, I think. So what this is it is an identity that is not at all obvious. And in fact, you can't derive this algebraically from the identities we've learned so far. There is an algebraic or a geometric argument that actually involves the distance formula, and it's very complicated. I actually prove this in trigonometry. I take the time to prove it. You don't need it proven here, but you do need to know that you got to be very, very careful when you use these. Okay, because it's not just a matter of like breaking this up and saying sine of A plus sine of B. Okay, it's not that at all. If you're going to use the identity and you have a sum here, then you have to write all this out. So sine of A plus B is sine of A times cosine B plus cosine A times sine B. Okay, and this is the same except if it's minus here, it's minus there. Okay, now for cosine here, these are the cosine of A plus B would be cosine A times cosine B, but this is minus here sine A times sine B. So both of these are the same trig function. Not up here for sine, they're sine cosine. Okay, but for cosine, this is cosines, these are sines. Okay, But this sign here is opposite. So if this is plus, that's going to be minus. If this is minus, that's plus. Okay? Otherwise, it's the same. And then the tangent is pretty complicated expression, but basically if you have tangent of A plus B, then it's like you can break it apart on top, tangent A plus tangent B, but then you have to divide it by 1 minus tangent A times tangent B. Okay? And for A minus B, this will be minus up here, but that'll be a plus down there. Okay? So it is very complicated identities. There is some patterns here. You could study them and probably kind of with a understanding, you know, have them, you can memorize them without just blindly memorizing them. Okay? But they do take a little time. So now I have just a few examples, and this is going to finish up what we're going to do with identities here. But here's some examples of how these can be used. So let's say I have sine of x minus pi over 2. Okay, well I could use this difference identity here. And if I did that, I would get sine x times cosine of pi over 2. Okay, that's sine A, cosine B. So in this case, the A is x and the B is pi over 2. And then if that's a minus, then this will be minus. And then I have cosine x and sine of pi over 2. And then as it turns out, this can be simplified, right? Because cosine of pi over 2 is 0. So this is really sine x times 0. And this is minus, this will be cosine x. And then sine of pi over 2 is 1 times 1. And so this whole thing becomes cosine of x. So this simplifies to that. See that? And this is actually another identity called the cofunction identity. Okay? As it turns out, if you have sine, or if you have any of the functions, okay, so, and inside you have x minus pi over 2, then it'll actually equal the cofunction. So, but don't worry about that. I didn't bring those up, but that is another identity. Okay, but you can derive it using the sum difference identity. And the homework actually asks you to do that. So, here's another interesting use. Pi over 12 is not one of our special angles, okay? But notice pi over 12 is like 15 degrees. It's half of pi over 6. So what I could do here is I could take a 45 degree angle and subtract a 30 degree angle, and I'd be left with 15 degrees, okay? But to do that in terms of radians, that would be taking pi over 4 minus pi over 3. So basically, if you put these over, if you actually combine these over common denominator, you will get pi over 12. Okay, well, what I can do now is I can use the Pythagorean identities on this. So this would be cosine pi over 4, cosine pi over 3. Okay, and then this is a minus, so this will be opposite now. It'll be plus. Okay, and then I get sine pi over 4, sine pi over 3. Okay, so now I can actually put values in for each of these because those are special angles. So cosine of pi over 4 is just square root of 2 over 2. Cosine of pi over 3 is going to be 1/2. And this is plus. Sine of pi over 4 is square root of 2 over 2. And sine of pi over 3 is square root of 3 over 2. Okay? And then I'm going to, I'll try to put this in here, squeeze it in here. So this here becomes square root of 2 over 4. And then I got plus, and then square root of 2 times square root of 3 is square root of 6. Square root of 6 over 4. And so I basically got this, square root of 2 plus square root of 6 over 4. So this is the exact answer for cosine of pi over 4. This is why we don't include that and memorize it on the unit circle, because it would get very complicated. Okay, but what's neat about this is you can use these sum difference identities to find exact values for other angles, okay, other than the ones that we initially started with. And there's some of those on the homework. So here's another interesting thing. If you have tangent of 2x, so I could write this as, and I'm going to bring it down here, tangent of x plus x, right? Tangent of x plus x, because x plus x would be 2x. And so now I can use the Pythagorean identity on this, but now a and b are both the same. So this would be tangent x plus tangent x, and this would be over 1 minus tangent x times tangent x. And then I could rewrite this. There's two of these, so that's 2 tangent x over 1 minus, and then this would be tangent squared x. And I would get this. And this is actually one of the double angle identities, which is the last thing we're going to look at. And they are clearly related to these, and this shows you how. A double angle identity is when you have a 2x inside, and it breaks it down so that you have a single angle inside. Okay, and that would be the double angle identity for tangent. So here's the actual double angle identities. Okay, sine of 2x is equal to 2 sine x cosine x. Cosine of 2x is equal to cosine squared x minus sine squared x. And then the tangent of 2x is equal to what we just got, that we found. So let's actually derive these using the identities. And maybe you might want to try this. So sine of 2x, okay, which is the sine of x plus x, right? Maybe you could pause the video and see if you can get this here, okay? And then start it back up and see how you did. Okay, so now I'm going to use the double angle identity here, and this is going to be sine x cosine x. Okay, this is like the a and the b, but they're both the same. And then the plus will be the same, and then I'll get cosine x sine x. Again, they're both the same, but now these are the same, because you could commute this around, right? And so what you really have are two of those, right? And that's where you get this identity. Okay, very similar here, cosine of 2x. Why don't you pause the video and see if you can get this here? Okay, let's see how you did here. So using the double angle or the sum difference identity for this here, they're both the same. They're both x's, and so I would get cosine x cosine x, and then it would be the opposite sign, so it would be minus, and then I would have sine x times sine x. Okay, and that's of course cosine squared x minus sine squared x. And so these are pretty easily derived from these sum difference identities. Okay, and I've always thought this was interesting, because if you have a cosine squared x plus a sine squared x, you get just one, right? That's the Pythagorean identity. But if it's a subtraction inside, okay, if they're being subtracted, you don't get one, okay? You actually get cosine of 2x, okay, which is a whole different identity. So let me show you one other thing, is that oftentimes this thing can be changed into two other possibilities by using the Pythagorean identities. So if I use, so what I'm going to do, I got, let me show you, cosine squared x plus sine squared x. So I could, this is equal to 1, so I could write this sine squared x is equal to 1 minus cosine squared x. And if I did that, and I plugged that in for this here, then I would get this, cosine squared x minus 1 minus cosine squared x. So I'm plugging that in for sine squared x. And then I got to distribute the negative sign. And that'll be plus cosine squared x. So now I got two of these, and I can bring them together, and I get one. Sorry. I got two of these, so I could bring those together, and I get 2 cosine squared x minus 1. Okay. And now I could do the same thing by bringing the sine squared x to the other side. So I get cosine squared x is equal to 1 minus sine squared x. And if I plug that into here for cosine x, then what happens is this. I would get 1 minus sine squared x minus sine squared x. And so basically I just combine those two and I get minus 2 sine squared x. Okay, and so what you can do, and oftentimes these are given when they list out the identities, is that you could also use 2 cosine squared x minus 1, or 1 minus 2 sine squared x. So in other words, cosine of 2x is equal to this, but cosine of 2x is also equal to that, and cosine of 2x is equal to that. So you could use any one of the three if it's useful. Okay. So there's a whole bunch of identity stuff here. You could do all kinds of other stuff. There's other identities, other stuff you can do. A lot of it is derived from these particular identities. These are the main ones, and you can do quite a bit with this, and we'll be using it in the course. So in the next set of videos, we're going to talk about solving trig equations.